Welcome to Lesson 14B, Filters, Part 1. Today we're going to talk about air filters, how they work, and how we can get some equations for their performance. So first of all, air filters are ubiquitous. They're everywhere. Furnace filters, engine filters, HVAC filters. These two pictures on the bottom left are from an air cleaner that I bought for my office. There's a pleated filter. There's a HEPA filter, this black one here. Face masks, of course, are filters. Here's a cloth one and a paper one. I also have a couple little demos that I normally bring to class. Here's an air filter, the kind you get from a furnace. This is from my furnace at home. It's just a whole bunch of blue fibers that are there, and then there's some strings holding it together. And then here's a different kind. This one's actually dirty. You can see the black dirt in there, and on the other side, a metal frame. That's just to hold it together because this thing's pretty flimsy otherwise. And then this is a charcoal filter. These black ones typically are either a HEPA or a charcoal filter. This one is designed to get rid of odors. As far as the categories or types of air filters, there's two basic kinds. The first one's called woven fabric. We say fabric, but it can be paper, cloth, even metal. Sometimes they have hairy fibers on them. You might have the blue cloths looking like that, and there's some kind of a weave pattern. Those are just basically for support. But then this is some kind of a yarn material. The main weave thread, either itself is like a yarn that has fibers, or behind this is just a bunch of fibers that are put together like that. The part of it that has the weaving is called a woven fabric. It doesn't have to be cloth. As I said, you can even have metal. And this one, it's a woven thread that's metal. And this would be for high temperature application. The second type is felt. So there's no kind of woven fabric. There might be some structural support weaving or some kind of a grid like I showed you. But felt is just a bunch of fibers that are randomly bundled together. And so here's some common examples. Any kind of a felt type filter like those furnace filters I showed you, just a bunch of fibers that are bundled together, sometimes glued together, sometimes they're just sandwiched between something. Like cigarette butt is a common one. You can see both a clean before smoking and a dirty after smoking. So the idea is to catch some of the tars and other nasty stuff coming from the tobacco burning before it gets into your lungs. Other classifications, HEPA filters you've heard of. Here's the official definition. To qualify as a HEPA filter, you have to have greater than 99.97% removal efficiency for a particular size particle, and that's 0.3 microns. ULPA is even better, ultra low penetration air filter, 99.999. By the way, some people will talk about nines. So if you say our filter is 6 nines or 5 nines, that means 99.999 is 5 nines. For a different size particles, 0.12. And then there's also MERV rating, and this is used by HVAC people. And this is kind of a strange one. It means minimum efficiency reporting value, but it talks about capturing particles greater than certain sizes. I haven't been able to find what the actual efficiency of them is. They're rated in these numbers. They keep getting better as you get a bigger number. MERV 1 to 4 are pretty crappy, and then you get some better ones. Permanently installed residential air conditioners, etc., have about a 5 to 8, and then you get into some bigger ones. MERV 13 is a very popular one, and you may have seen in the news that MERV 13 is recommended for coronavirus. If you read articles about buying an air cleaner, often they'll say you need a MERV 13 or better. This last one, 17 to 20, are used for things like clean rooms in hospitals and manufacturing. This MERV 13 is interesting, just to comment that the coronavirus itself, they're about 0.1 or 0.125 microns. So it's not clear to me why a MERV 13, which removes particles greater than 0.3, is going to be real effective for coronavirus, but that's what everyone seems to be claiming. I want to talk about the operation of air filters. Here's what most people think. You take a filter like a window screen, and then here's a bug, and the bug is too big to fit through the hole, so it blocks the bug from coming in. That's how people think filters work. And they do work that way for big particles. But it turns out that filters can remove particles smaller than the opening. So in this case, this opening size here, most people would say, well, you can't stop any particles smaller than that, only particles bigger than that. But you might be able to stop actually particles that are smaller than that.
Then, sir, how do these air filters work?
Thank you, Boris. I was hoping that someone would ask me that. The answer is something we've been talking about, and that's inertial separation. Suppose this is a fiber. So df is the diameter of a fiber. So if I go back to these pictures, df would be the diameter of one of these fibers. So an average diameter of the fiber. This kind, you'd use the actual diameter of this metal wire. And in here, you got kind of a double thing going on. You have this woven material, this blue part, but you also have some fibers. So you'd use this diameter for one analysis, and you'd use the diameter of the red fibers inside as a different diameter. But suppose we call that df. So we have some fiber, and it's a cylinder basically, df, and suppose it's aligned perpendicular to the flow. And now you have some flow coming in with some airspeed u. The air streamlines look something like that, and the particles will come along. And so this particle, for example, encounters that sharp turn, and it cannot make that sharp turn, so it smashes into the fiber. Now, we make the assumption, that's a pretty good assumption, that the particles stick to the fibers when they hit. So there's a bunch of cohesive forces, and there's also static electricity. So that's a pretty good assumption. So some of those particles will hit, and there are some particles that are a little bit too far away so that they miss. They don't get collected. But that's why we have a bunch of fibers, because if it doesn't get collected there, it might get collected with the fiber downstream, get caught into that fiber. And so you have a bunch of fibers in series, essentially. You have a whole bunch of particle collectors in series. That's the basic way that it works. So the answer is inertial separation. So let's do an analysis. Here's our filter. It has some length L, and I'm going to analyze it as X starting from the beginning to X equal L. The flow is from left to right. We're going to call this U naught. Assuming there's no leaks around the edges, that same amount of flow has to go through the filter so it comes out the other end. A couple things of interest here. First of all, the airflow speed inside the filter itself, we're going to call U, and U is greater than U naught, and that's due to blockage. So there's all these fibers and they're blocking the flow. So the average U inside the filter, which we're using for this analysis, is bigger than the U naught that's actually in your duct coming into the filter in the first place. We're going to take a thin slice at some X location. This will be of dimension dx. So this is a control volume. And we assume that it's well mixed vertically. There's no difference in the concentration here versus here versus here. But C is changing with X. So we have a C and we have a C plus a DC at X plus dx. And in this case, DC would be negative because the concentration will be decreasing as you go through. So you have some C in and you have some C out. It's an air pollution control device. It's a cleaner. So C out is less than C in, and we can define some efficiency of the filter just like we always do. Let's define epsilon as the porosity of the filter, and that's defined as the open fraction of the material, and F sub F is called the blockage of the filter, and that's equal to the blocked fraction. So when I showed you that blue furnace filter from my house, you could actually see through it. The percent open area would be the porosity, and that might be 70, 90%. Blocked area might be only 30 or 10% because these two are related. FF is 1 minus epsilon. We can write epsilon in percent and FF in percent in typical units. If epsilon is 90% open and FF is 10%, but to use in equations, we would use epsilon equals 0.90. Because of the blockage, U is bigger than U naught. In fact, U is equal to U naught over epsilon. Since epsilon is always between 0 and 1, we therefore have a bigger U than we have U naught. So let's take this control volume, and if I had enough time, I could do the math, but you get, as you might have expected, a first order ODE, just like we've seen several times in this class. If I sketch C, mass concentration, as a function of X, and again, X goes from 0 to L for the filter. L is the thickness or the length of the filter. And what would C look like? Well, we'll have some C in, and we'll have some C out. It would look something like this. It would be a first order decay. And so C in would be at X equals 0 and C out would be at X equal L. If I keep making L bigger, I would keep going down, down, down until eventually it would go towards 0. We can get a result, just like our other equations for first order behavior, C out is equal to C in times E to the negative L over LC. And then you can make an eta out of that. Eta of the filter is 1 minus C out over C in equal 1 minus EXP negative L over LC. And these would be all at one diameter. So we would use eta of dP as a grade efficiency, since this curve would vary with dP. The only thing left here is this LC. LC is a critical length. Now you should recognize this. This is exactly the same equation as what we had for gravimetric settling in ducts, where we were able to calculate that critical length analytically. So here it's the same equation. We just have to figure out what critical length is. So we need to get an equation for LC in order to be able to use this expression. How do we get LC, critical length? There's several models, and the only one we're going to talk about is the Calvert and Englund model. The C&E model models inertial separation only. Okay, it doesn't deal with Brownian motion. What we define is a single fiber collection grade efficiency. Take one fiber, that's my filter, just one string basically. And I look at a bunch of particles that are directly in front of the fiber. And so we count them, say there's 1,000 of them, and then we look at after the filter, how many particles are here. So in other words, how many of them got collected, and that will define your eta dP. So eta F of dP is the single fiber collection grade efficiency because it's a function of dP. So it's the fraction of particles collected from directly upstream. And this is due to inertial separation. If you have just one fiber, one string as your filter, it's not going to be a very good filter. In fact, the eta F is pretty small. This is defined in terms of a STK. What's that? That's called a Stokes number. It's non-dimensional. It's the ratio of the characteristic time associated with the particle motion over a characteristic time of the flow. In order to calculate it, you need air properties, rho, mu, and the speed of the air. You need the particle properties, dP, rho, p, and you need the filter properties, which are dF and epsilon, the porosity. And those would usually be known. We know all these things, and then you can calculate the Stokes number. Also, you need to know the length, because that comes in later when we get into the grade efficiency. Now we define a critical length, and it turns out with this Calvert and Englund model, we have a nice expression for LC, which is given here. In terms of DF, fiber diameter, your single fiber collection grade efficiency, your porosity, and you can calculate LC. Once we have LC, here's our final equation for the grade efficiency of removal. Here's our fiber, DF, and a U coming in, and there's some streamlines. And suppose this particle is a very tiny particle that just misses that fiber. It doesn't have enough inertial separation. This Calvert and Englund model is based on this inertial separation, and it would say that particle is not collected. However, there's also Brownian motion. Brownian motion makes everything go in a random pattern, and so it leads to greater eta F than Calvert and Englund model, which includes only the inertial separation. The bottom line is that C and E model underestimates eta. So it's kind of a conservative estimate. And when you start getting into really tiny particles, you can actually get better collection because of Brownian motion.
This all seems strangely familiar. Didn't we talk about the same thing with raindrops?
Yes, good observation, Mr. Bernoulli. With raindrops, we had flow over spheres, whereas here we have flow over cylinders. But the physics is pretty much the same, and so are the models.
A quick example, here's an air filter that's used to clean dusty air. And I give you the properties, the fiber diameter, these are the hairy fibers, U naught, epsilon porosity, dP, particles that we're interested in or targeting, the density of the particles, L is the thickness or length of the filter, and then we have this air at SATP. So let's calculate the collection grade efficiency of the filter for these particles. The first thing I would do is start with the Stokes number. So I put in all the numbers and I get a dimensionless number, and then I calculate eta F and I get about 0.723%. So that's very tiny. One fiber doesn't do a whole lot. That's why you have to have a thick filter. The thicker the filter, the better, because you get more of these fibers that particles have a chance to hit. Now we need to do the critical length, LC. So plugging those numbers into here, I get my critical length, 6.88 millimeters. And now finally we're ready to calculate eta dP. After plugging in my numbers, I get 0.516 or 51.6% for this particular diameter particle, which is 1 micron. And now you can repeat for a range of dp. You would expect a grade efficiency curve. So if we plot A to dp, we would expect to get something like this, a typical S curve for a grade efficiency like we're used to. We could also define a cut diameter. So that's how you deal with these filters. I have just one more comment here. The Calvert and Englund model does not include Brownian diffusion. And so the actual grade efficiency curve will go up because of Brownian motion for very, very small particles. Here's some experimental data for an actual filter. Turns out that for big particles, when I say big, we're talking about particles here that are supermicrons, so bigger than about a micron. Inertial separation dominates. So the Calvert and Englund model would do great. For very, very tiny particles, less than 1/10 of a micron here, Brownian diffusion dominates and inertial separation is pretty negligible. So the S curve from Calvert and Englund would continue down like that, but the actual one dips back up and you can have almost 100% for the really, really tiny particles up there because of Brownian motion. This is actually two different velocities here. So the higher velocity has less efficiency than the lower velocity in this case. The 1 centimeter case has very high efficiencies up here, about 97% even in the dip. But the problem is there's a dip, and this dip is kind of unavoidable for filters. And it's typically centered around 0.2 microns, typically between 0.1 and 0.5. This whole dip is in this range of between about 0.03 to 1.3 microns on this plot. And so that's why air filters are tested with 0.12 or 0.3 microns, since this is where the dip occurs. So 0.12 has been picked as a standard, and 0.3, which is near that dip. These are the hardest particles to collect in that range. So that's why HEPA filters use 0.3 microns. ULPA filters use 0.12 microns as their particle, because for this very reason that those are the hardest ones to collect. In this zone, I have that red egg around. Neither of these is very effective. Inertial separation doesn't really work well, and Brownian diffusion doesn't work well because the particles are too big. Particles are too big for Brownian, too small for inertial, so there's that dip. And so that's why they test these there. MERV+13 uses 0.3, and unfortunately, coronavirus particles are right around this size right here, and for most filters, you're in that dip. It's very hard to get rid of these very small virus particles.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.